Okay, so I'll talk a little bit about academic efforts on formalizing GQL. And so the standards are great, they're fantastic, but not necessarily if you're an academic. And because let's say you want to write a paper about pattern matching that we have seen, and you say, okay, where's the definition of pattern matching? So let me look at the standard, let me look at the syntax, and you see this page, and then see this page, and then see this page, and this page, and this page, and it's still the syntax, right? And then I'm halfway through, so then you see this page, you see this page, you see this page, you see this page. Okay, you're done with the syntax, so basically your page limit is completely over. You haven't done 20% of your definition one. How are you going to write the paper? Okay, so and then you again as an academic, so you try to work with the standard. So okay, I mean I've been doing this game now for 5 years. I'm just about to sort of getting professional at understanding how the things are. And if you're an academic, it's like a little bit, okay, can you find the rabbit? No? Okay, yeah, that's what usually happens. Okay, so here where we come in and actually tell you what the rabbit is. Okay, so what's our goal? So we want basically it's equal to the masses, but the masses of academics. And so what we want to do, we want to distill the standard. We want to formalize it. We want to provide the semantics so that people would actually know what the things mean, rather than reading what's called general rules, which is good for implementers, but not so good if you actually want to do research on that. And obviously, we do initial results because we also want to publish papers. If you just publish paper, do paper with a definition, that's not going to get in. And also, you know, explain what's similar and different, sort of from database research point of view, which concentrates on regular past queries, conjunctive regular past queries, nested regular expressions, regular queries, and so on and so forth. Okay, and also outline the research challenges. So tell the research community, then, you know, stop writing another dozen papers on RPQs in scenarios that nobody cares about, but do something useful. So the word of caution, of course, with all this work is that GQL is a moving target, right? So it's a little bit tricky. So there was a good example of that, after we sent the camera-ready version of one of the papers, the next day, literally next day, the WG3 invalidated syntax in one of those papers by changing one of the keywords, right? So we've done a few things now. So last year, there was a paper in SIGMOD on pattern matching, which was written by WG3 plus members of the formal semantics working group, which is kind of this Schrödinger group. So it exists in real life. It's something that exists in practice, but not in theory. So because I'm told that this group was eliminated by LDBC, but we still are and we still do work. We still exist and we still do work. Then in pods, that just happened. So there was a paper presented on the formalization of pattern matching, on the common pattern matching that we heard about. And also it was a subject of my KR23 keynote when I sort of try to talk to people working on, there was a big part of KR, the leading conference on logical AI and knowledge representation, and quite a few folks that work on knowledge graphs, knowledge representation. So I was trying to convince them to start using this model rather than RPQs. And also there was a joint LDBC ICDT keynote in which I presented the formalization of GQL, plus there was a paper, accompanying paper in ICDT proceedings so that people could actually look at that and work on it. Okay, so what's GQL in a nutshell for academics? Of course, we already know this. It's pattern matching is the core, and pattern matching takes a graph and throws it in a table. Then on top of this, we have relational querying, right? These are usually relational operators, a little bit more. So I'll say a few words about that. And so how you can combine graph and a table, essentially. That's something that goes beyond pure relational querying. And then updates, but we haven't touched yet. So updates we haven't looked at, and updates are tricky, as we already know from trying to formalize Cypher updates a few years back. Okay. So what's the core? So the core is a graph pattern matching. So you take a graph and it produces a table. And this is just what was presented in pods. And essentially, so just when I do like in a single slide, this pattern calculus in a nutshell. The way I think of this bit of work is as follows. Imagine that the first database language ever produced is SQL. And the first thing ever describing database language to you is part 2 SQL Foundation already mentioned. And then somebody asks you to write Code's original paper and tell the rest of the world what is relational calculus and what is relational algebra, right? That's what we sort of had to do. We had to, do the history as it should have been, right? And being a Russian, I'm actually quite good at rewriting history, so that's what I'm trying to do here with my group. So okay, so what I'm going to do, I'll present you and just to explain to you what the calculus, what this basic underlying pattern calculus is, and this 100 pages get distilled to one slide. So we have node patterns, right? Like written here is cipher style. So we have a variable, potentially label. So it just matches an labeled node assigns to a variable. We have the same thing with edges. Edges could be directed left, right, or undirected. And of course, and both variable and label are optional. So we know again that from cipher, for example, that you can just match we can match a node, but you don't have to assign it to a variable. Then we have patterns. What are the patterns? So the patterns are, we have a node, we have an edge. We can concatenate patterns, we can union patterns, we can repeat the patterns between n and m times. And n and m could be infinity, so we have the linear star. And we can selection with a condition. What are the conditions? We can compare the property values. So if you have like an edge, x dot a is a value of property a in that node or edge, we can compare them and we can close on the Boolean combinations. Again, think of trying to distill this to the level of relational calculus. In the first level of relational calculus, I'm not going to give you like the trigonometric function or anything like that. I'm just going to, think of textbook version. I'm only going to be talking about equality. Right? So, and then the queries themselves. So it's either we have some kind of restriction or on the set of patterns that we output to ensure that there are apparently many of them. We can name the patterns and we can join the results. And this is basically it, right? So it's just one slide, and this is it. This is really the core of the language. So then, of course, what we did the semantics. So what's the idea of the semantics? Just pictorially, so we have a query that is a join of a bunch of patterns, maybe with some restrictors that tell you what restrictors are the usual ones, like things like trail, simple, shortest. And we have a bunch of variables. And then a match results not in tuple plus, in a set of tuples of path plus a table. So basically, every time we have a match gives you a path. Intuitively think of that as a path for each of the pattern, plus a record in a table. And then SQL and GQL and SQL PGP work with the table, right? So this is how you get the table. Right. So what's in the table? So in the table, the entries could be graph elements, there could be nodes, there could be edges, there could be path, because we can even path a name, so we put them in a table. And we also have lists of graph elements, right? So what do we get lists from? So we get lists from here. So if we have here some repetitions inside, then basically as your pattern gets matched and you repeat the pattern several times, every time you repeat it, you have binding, right? And this binding goes into a list. So this way you can write a very clean semantics. It doesn't take long. So, and this you can really use your definition one, right? So you can study from there. So tables may also have nulls because of disjunction, right? So if you match one part of the pattern but not the other, then you get a null. Now, what we've done in the post paper, we gave formal semantics for well-typed expressions. So we gave a simple type system that tells you when a table contains graph element, list, when a null can appear. We did the complexity result. So we showed for the more research-oriented folks here that p-space data complexity of enumeration. Of course, at theoretical conference, you get murdered for that because they say, well, it's not going to work. But of course, we know that ciphers and p-hard and it works. So, there are things that actually work in practice, but not in theory. And expressing and expressibility. So it basically subsumes pretty much everything that existed before. So then, of course, from that point on, we go to relational querying. And again, thanks to Stefan, who already showed that, and to Keith, who showed some examples. So we have these things. We have return, which is a projection. You can think of the projection or output. We have let that adds columns. We had filter, which is a selection. We had for unnesting for lists. And you can do another match that does a match and joins with the existing table. And we have the usual set operations like union, intersect, except. You can do otherwise. So if one query is not empty, it return. Otherwise, the second one is return. And then you can use multiple graphs, again, as was shown, right? So you can say use one graph, then do your match where return, then next you use another graph, match where return, and so on and so forth, right? So you can, it's not a single graph, right? So as was used in pattern matching, but you can, in GQL, you can actually change graph and do different matching between graphs. So then what we've done in the ICDT paper is, it's called the Researcher's Digest of GQL. So the idea that in a syntax closer to GQL, but still simple enough for people to understand what's going on. So we presented this language and we gave the formal semantics, right? So this was the syntax of the pattern. So you see it's kind of a little bit, looks a little bit more GQL-ish the way we presented it there, but it still fits on one slide in slightly smaller form this time. And it's the same as we had before. The only difference is really we added exists as a condition to subqueries. And then the rest of the queries. So we have clauses, which is things like match, let, for, and filter. Then we have linear composition. So you can sort of build the things linearly in the cipher and GQL style and GQL return style. And then we have the queries themselves, which essentially use a graph, then do several queries, and then use another graph, do several queries, and so on and so forth. And the core of the ICDT paper was to give the semantics, right? So, and the semantics is just this, right? So it's 2 pages. So this is something that researchers can sit and in an afternoon understand, decipher, and start working on. Okay. So the paper omitted, of course, a few things because, you know, you cannot distill 550 pages into 4, right? Otherwise, what was the committee working on all these years? And so and again, in sort of the spirit of going from, you know, real language to reconstruction, so we omitted the bag semantics, so everything that you have to multiplicities. We didn't add aggregation. Again, the first textbook on relational databases will talk about relational calculus. It will not include aggregation in relational calculus. We omitted procedure calls, updates, and you know, some past, not all past modes were included, and things like catalog operations, data types, and so on. And the reason of doing this was actually to bring it to the attention of the database community. And so, you know, the first version of the standard will be published in 2024. And then this is the time to sort of stop and pause and say, does it all make sense, right? So, you know, if you look at something like that, it looks fine, right, at first glance. Then you start looking at that and say, well, okay, maybe there are a few things to do here, right? And that's what we are suggesting to the research community. You have to start doing research into stuff now, right? Essentially to understand, is it good? Is it usable? Is it the best because everything else is average, as they say? Or, you know, is it this stuff, or is it something that you can use more realistically? And I'll give you 3 lines of directions. So one of them is of direction of research that I'm trying to sort of advertise this community to the research community. So one of them is comfort zone for theoreticians, right? Basically stay in your comfy couch, you know, don't leave home, you know, do things what you've done all your life. And it's still very useful, right? Because we need to know these things like, you know, clean sub-languages. In the relational database, you know everything about conjunctive queries, reunions, data log, you know, database folks are really good at that. And also query optimization, containment, equivalence, practical algorithms and data structures, and so on. Then there are sort of work on extra features for the language, right? So then, you know, we have to look at some different features. And for example, updating graphs, right? We haven't touched that, and it's not a trivial matter. We already explored quite a few alternative semantics in the context of cipher updates. And also design decisions, so basically alternatives and extra things, like how we deal with group variables. You know, I'm personally unhappy that we create this list. To me, I think this could have been avoided. Obviously not in version 1, but in the future one could think about it. Also, non-local variables can be used variables outside the context of current pattern to look at conditions. Like here, you know, in this condition inside an edge pattern, I actually use, and it's a pass pattern, right? There's a clean star, but I use this guy X from outside, right? So, right. So what are the implications for complexity? We don't know this. So, and finally, essentially what's missing, right, in all of this, and to me, the biggest thing that's missing is graph-to-graph queries. So GQL is still an engine for turning graphs into relations, and we have to understand how to turn graphs into graphs. And Stefan mentioned that briefly when he said about graph projection, graph views. I mean, without that, we cannot do views, which we are so used to in relational world. And on schema things look a little bit better, right? There has been work and there is very active work. So things are actually happening. Okay, and just final thoughts. So after these 6 years of work, or 5, 6, depends how you count, GQL will become a standard. But you know, all my Polish friends are gone. Or not all of them, but I would quote from Jerzy Lec, when said, "When you jump for joy, beware. When you jump for joy, beware that nobody moves ground under your feet." And because you know, NDL was also standard, right? But it didn't leave a lasting impression on the community. And what's happening here that there's graph stuff on the GQL side, and then there's a relational view of things, right? So, for example, SQL PGQ is going to be implemented in a relational system. Then there, you know, in RelationalAI is looking for relational language for knowledge graphs. And in general, there is debate, right? So there was the debate in the register article in the register in March, right? The great graph debate, is it a revolutionary concept in databases or just a niche curiosity? And I think the research community has actually a lot to say about this. But now that we kind of what we are doing, we've been giving them tools to finally start saying that rather than just follow what the practitioners are saying. So that's. And finally, you know, to do this stuff, it takes a lot of people. So that's the team. Thanks very much to everyone in the team. And because to distill this 500 pages to something that researchers can use, it's and to one slide, it takes a lot of time. All right, thanks. Yes, please. I think the idea is to use this mic.
Yes, please.
Yeah, so that the Zoom participants would hear.
Yeah, first of all, thank you, Leonid, for providing this interesting talk. I've been doing pattern matching for over 10 years, and for God's sake, and today we have a formalization. Thank you very much. We appreciate your work. And actually, you mentioned about you know, compare graph query with SQL. And you know, as a guy that I'm doing graph queries and graph query optimizations, the more question that frequently encounter and ask was how to graph query compare to SQL. As you can obviously, you know, if there's an equivalence somehow that graph pattern matching, for example, vertex to an edge is equivalent to a fixed join, right, in SQL. And obviously, if you turn everything of graph into SQL, you can leverage directly the relational algebra and all the optimizer they have done in SQL for over decades. So I want to hear your point of view. If we treat graph as a graph natively, what benefit do we have, and how can we dig into this thing? For example, to develop a graph-specific optimizer, such something. When I really want to hear your suggestion, your point of view. Thank you very much.
Yeah, it's actually a very good question. So of course, you know, if you just look at this pattern matching, right? So as I said, you know, you can just you can do simple pattern matching with usual joins. If you throw in a clean star, then you need recursion, and this pattern matching can be translated in SQL, in recursive SQL, right? So how they perform? For several people in this audience, that's our favorite subject that we give to our master students for projects, right? I can see some people smiling here because they recognize themselves in this group. I know that it's great, you know, you just give it like to 5 students and then you're done with the project for the summer. I don't have good conclusions yet. You know, there are things when things work, things when things don't work. So I think it actually requires at this point probably a PhD topic rather than a bunch of master topics. It's really hard for me to say. So there's kind of anecdotally recursive SQL doesn't perform well, but then some people manage to actually tune it. So it's really to me this is something that people should be studying, should be looking at. So I don't have the answer, but I fully agree that's a very good question.
That's implementation specific, right?
Yeah, of course it's
So
implemented.
It's not a conceptual concern.
No, it's concept. If all implementations of recursive SQL behave badly, then it's conceptual concern, right?
Sure, but SQL didn't work on all-out queries in the 80s, and they made it work on all-out queries in the 90s. It didn't work on BigQuery workloads 2000s, and it was all going to be a hoop. And then we made it work on, so there is a point of view that you can just sort of look at the beauty of the models that separates, conceptual from the implementation. You can find new data structures, architecture, join algorithms, optimization approaches to make it work, right? So,
Yeah, and for example, one piece of work I would suggest that you look at is a work coming from Chile. It's called Millennium DB, right? When these guys actually achieve quite good results, and precisely because of smart implementation, and they run clean star queries, and they use worst case optimal joins, not surprisingly, to achieve good results. Yeah, this is already published, right? So it's Domagoj Vergoch. So it's this guy and his team.